I'd like to take a moment to think carefully about an object that is more complex than a point mass, an extended body that is deformable, that is, you can change its shape when you apply a force to it. So a deformable body and a useful concept called pseudowork. So we're about to step off a cliff at the edge of Newtonian mechanics, but then we'll be pulling ourselves back at the last second. So the work energy theorem, as we know it, applies to a point mass and only to a point mass. We derived it by assuming we're working with a point mass. So can we use it for an extended body, something that has volume and shape and dimension? For instance, if we have a block colliding inelastically with a rigid, immovable wall. Inelastically means it's not a spring-like collision. It's not a bouncy collision. It's just going to smack into that wall and come to rest, let's say. So here initially is our block with a center of mass. Normally, we would like to just approximate this extended body, this whole block, as just a single point mass located at the center of mass, and let that point mass hit the wall and study that collision. So we want to know if that's possible here. Can we use our work energy theorem, which applies to a point mass, to this extended body? The work done on the point mass block, this point mass approximation for the block by the wall. Okay, so the work done by that contact force when the point mass contacts the wall is given by this integral. Now, for the block to remain in contact with the wall so that we actually have a contact force, the velocity of the block must equal the velocity of the wall for some time. That is, if the velocity of our point mass here is still positive, or still to the right when it hits the wall, it'll be going through the wall. If its velocity is to the left, it'll be leaving the wall and will have lost contact. So if it's not in contact, there's no contact force and there's no work being done. But if it is in contact, its speed must match the speed of the wall, but the speed of the wall is zero. The wall isn't moving. I could replace this dr right here with v dt, since I can rearrange this definition here. So this dr I can replace with v dt, where v is the velocity of the block. And for the block to stay in contact with the wall, its velocity has to match the velocity of the wall, which is zero. And if it's not in contact, the contact force is zero. So I'm arguing here that the work integral is going to be zero. An immovable wall cannot do work because it cannot push over a distance. To do work, you have to apply a force over a distance, and that wall does not move. It also can't do work because it cannot accept kinetic energy if the wall can't move, and the wall has no stored energy to transfer or give to the block. Remember, work done by a force represents an energy transfer by that force. The wall has no energy to give to the block. So our immovable wall cannot do work. But we know that there is a change in kinetic energy. Our block does come to rest. So if the immovable wall can't do work, then there must be something inadequate about our point mass approximation for the block. So we're going to have to try to treat the block as an extended body to figure out where the work is being done, the work that changes the kinetic energy of the block. If the wall isn't doing that work, where is that work happening? So let's imagine our block approaching the wall here, and I've sort of sliced the block into a number of thin little slices, each with a, you can imagine, infinitesimal mass dm. So this pink slice is located right at the center of mass, this orange slice somewhere over here, and that yellow slice is the thinnest little slice of mass on the right edge of the block. And initially, as the block approaches the wall, moving as a single rigid body, all three of these sections would have the same velocity. So they're all moving with the same velocity as we approach the wall. Then, once the right end contacts the wall, here in red is the contact force from the wall acting on the right end of the block. As soon as the block contacts the wall, there will immediately be a large force on that yellow piece of mass, bringing it quickly to rest, so it remains in contact with the wall. So that yellow bit of mass has velocity 0, so it stays in contact with the wall, which has velocity 0. And a key point here is that the wall is pushing on that yellow bit of mass at the edge of the block. The wall is not directly in contact with this orange bit of mass, and the wall is not directly in contact with this pink bit of mass or any other part of the block. The wall can only exert a force on something it's touching, and it's only touching this little bit of mass at the edge. So, running time forward a little bit more, the block is going to start to compress. It'll crunch. It'll accordion. This is our deformable extended body, changing in shape as it smashes into the wall. And as soon as it contacts the wall, it starts to slow down, but the parts closer to the wall are going to slow down more rapidly. So here in this picture, already by this time, the velocity of the pink section is greater than the velocity of the orange section, and the velocity of the yellow one is already 0. So the pink is going to be overtaking the orange, which is going to be overtaking the yellow. So here a moment later, we've seen that happening. That's the accordioning of our block. At this point, pink is still going faster than orange, which is still going faster than yellow. So we've still got some more crunching to do here. Now, the little bit of block, the yellow bit that the wall is actually acting on. The wall does not act on this dm over a distance for the same reason we discussed a moment ago, that the wall cannot do work on the point mass touching it because the wall cannot push that little point mass over a distance. Likewise here, the wall cannot push that yellow point mass over a distance, so there is no work done by the contact force on that yellow bit. The dr, the displacement for that yellow bit, is 0 since the little yellow bit is not moving. But the contact force does act on that little yellow bit of mass, that little dm, over time. Since time passes from this moment to this moment, the impulse imparted to that yellow dm by the wall is a non-zero result of this integral here. So that contact force acting over time, this is non-zero. So I'm going to sort of put this idea to the side for the moment. It's a key realization that we're going to come back to later, but for the moment this is an aside. Okay, so remember what we're trying to do here is figure out where the change in kinetic energy is occurring. Where is the work being done on the block if the wall is not doing work on the block? That's what we're trying to figure out. So let's look at one of those little bits of mass, the orange little bit dm right there. Let's look at this dm. And imagine the two little slices of mass on either side of that orange slice. Let's call them 1, 2, and 3. So the orange bit is mass 2. So at some moment, say here, as the block is crushing itself into the wall, that orange bit has a velocity v2, and it's being pushed by the two bits of mass on either side of it. A little bit here and a little bit there. So there's the force on 2 due to 3, and the force on 2 due to 1. We know this force has to be greater in magnitude than this one, so the net force is to the left, slowing down our little orange dm as our collision progresses. So the net work done on this little slice of mass, this little dm here, will be this net force dotted with the displacement of that little slice of mass. And we see that since our net force is to the left and our displacement will be to the right, that's a negative work being done on that little dm there, our little orange dm. And according to our work energy theorem, which we can safely apply to this little slice of mass because it's so thin we can treat it like a point mass, and we know our work energy theorem applies to a point mass. Therefore, this negative work done on the orange slice by its two neighboring bits of block, that negative work reduces the kinetic energy of that little orange slice. And where does that kinetic energy go? Into non-mechanical energy, of course. Heat and sound and deformation, meaning a rearrangement of the atoms as the block changes shape. That'll require some energy to accomplish that. So the work being done on the block, the work that's not being done by the wall, we know the wall isn't doing that work. The work being done on the block is being done internally by different parts of the block moving at different velocities, pushing on each other. That's where the work that slows the block down happens. It's happening inside the block itself. With this piece of block pushing on that piece of block and pushing on that piece of block, each little piece will have a slightly different velocity. That's why it's scrunching up here. So the pieces are moving, so these forces, each little piece is moving at different velocities. So these forces will be acting over distances. So these forces acting over distances, there's where the work is happening. It's internal, inside the block itself, like an internal friction converting the kinetic energy of the block, converting the kinetic energy of the block into heat. So our work energy theorem, in fact, doesn't apply to an extended body undergoing an inelastic collision. This is the answer to the question we posed here at the beginning. Can we use the work energy theorem for our extended body? We now have our answer. And the answer is no. Looking at our work energy theorem, the net work is this integral here, but the net force will be different on every little bit of block for every little dm. And the force here, that velocity vector there, v dt, recall, is just dr. I replace that with v dt in this integral. This velocity is different for every single dm. And over on the right-hand side, this is supposed to be the change in kinetic energy, but the velocity of each little dm is different. So how would you even do this integral? It's too hard. Too hard to apply this to an object made up of zillions of little dm's, all with different net forces and different velocities. So we've hit a cliff. We have reached a boundary of classical mechanics here. It is too hard to try to apply our work energy theorem to this extended body undergoing an inelastic collision. We would need new physics to proceed here. In fact, we would need thermodynamics to fully appreciate the energy transfers going on inside an extended body. But there is another way for us to approach this collision using the physics we know.